Alright guys, I just ordered some black markers, okay, so that next time we won't have that red marker that some people told me it's a bit hard to read. Alright guys, oh, I forgot to delete the board. Let me delete the board from the last lesson, then let's start. Alright guys, we're ready. We are ready. So last time we talked about random number generators and pseudo-random number generators. So we're gonna keep continuing to talk about pseudo-random number generators, but we're gonna talk about real world examples, okay? So let me just fix the camera a little bit. So pseudo-random number generators. Okay, we know what they are, right? What they do. And now in the real world, obviously in practical applications, where do they live? Obviously, they live inside operating systems of any kind. Your computer's operating system has one. Your phone operating system has one. Your little fitness tracker device, smart device, has one. Your IoT toaster has one. Every electronic has a pseudo-random number generator inside. So, and sorry the mess guy, I forgot to put it away, but we're doing some work in the office and it will be gone tomorrow. So basically, it lives into operating system of every electronics, and it's basically implemented in two ways. In a software way and in a hardware way, okay? We're gonna start talking about the software implementations, okay? And then we'll move on to the hardware one at the end of the video. Also, we're gonna move to the computer after I finish the software part. We're gonna look at actual real pieces of code that implement pseudo-random number generator, so I hope you're excited. So, what is in Unix? Let's talk about software pseudo-random number generators in Unix, okay? Perfect. So in Unix we have a file, you know, everything in Linux is a file. We have a file at the root, folder dev, and file urandom. Okay? Urandom is a file, right? Why these don't look like? Urandom is a file, so guess what? You can read it as a file, and guess if you read it as a file, what are you gonna get? You're gonna get reliable random bits directly from the operating system. So we can say read file at the path dev urandom and get me 10 megabytes, right? Read 10 megabytes out of this /dev/urandom, and what I'm gonna get back is 10 megabytes of data of random bits, random bytes. And so that's how it works in Unix. And so right after we're gonna move to the computer, I'm gonna show you a naive way let me see if I can call it naive code implementation. And a actually proper. The naive one you're gonna see is very short, and it's something that I and you and everyone would write if we're trying to implement a function that gives you random numbers, but it's gonna be very insecure because it doesn't do all the checks that the proper code implementation does. That's and we're gonna see, well, I'm gonna come back to this after when we go to the computer. And so Let me see what's the next Go version. Okay, perfect. Now, perfect. How does this dev-urandom work? So basically, there are raw entropy bits that are harvested from keyboard movement activity, mouse movement activity, disk, hard drive and disk measurements of the operating system. All these, which are pretty random, like the way I move my mouse can be random, unpredictable. The way what I type can be anything, and the disk operation, it's random measurements. This is a reliable source of randomness, and that is what gives those measurements from the operating system give raw random bits, which are then, let me see how I can illustrate this. So we have raw bits, right? And these raw bits, these raw bits are going to they come from, actually make an arrow, keyboard, mouse, disk, input, output measurements, whatever. They're measured, sampled. You get raw bits with high entropy, random raw bits. So what happens is that the Unix kernel takes the UDEV takes these raw bits and it does a hashing function, which we haven't gone over yet. But hashing function basically means that you take an input and you shuffle them, create a signature, and create a fixed size signature of those bits. And this gives the pseudo-random data, the bits that we want. And I would even write reliable, okay? So the raw bits are read from the sampled from sources from randomness, high entropy, and they're hashed into pseudo-random bits. Why are they hashed? Because from a few bits you create more. Because every time you do the signature of the SHA signature of something, you're always gonna end up with a fixed amount of data. Okay, so and we'll see SHA and hash functions later in the book. So what's the deal with this pseudo-random generator? Do you remember that pseudo-random generators have this thing called entropy pool? Very good, they do. So this one is also going to have, this Unix implementation of the pseudo-random number generator also has an entropy pool. And that is, let me see, I can write it below bottom. Yeah, already here. And that is an entropy pool of 512 bytes. Okay, so it has an entropy pool 512 bytes big, and it has two types of pool, or I don't know if the same pool divided in two times, but the point is that you have Unix, you have two types of pool. A blocking pool, let me do it from here. We'll see why it's blocking. Oops, no way, right? Poop, guys. And non-blocking. That was a nice Easter egg for people that actually watch the video. Non-block. CK. King. Pool. There you go. I had to think about it. Why is it a blocking and a non-blocking pool? Because we have two different files actually, interface that we can query. One is urandom, the one that I mentioned before. Oopsie. I'll write in lowercase. Urandom. Well, this one is clearly random. Okay? What's the difference? The difference is that the non-blocking pool, whenever you read from this, will always return random bits. Okay? Will always return. Nothing blocks this operation from giving you random bits. But the blocking one, instead, will not give you random bits if a procedure called entropy check fails. What is an entropy check? An entropy check is a check, so an operation that gets performed on the entropy pool, and basically this operation determines the amount of entropy present in the pool. So if the pool is full and it's full of random bits, then we have an entropy check a high entropy value. The entropy check is passed, and so the operating system is going to give us the random is going to give us bit. But if we've been using, for example, the function a lot, and it's been reading a lot from these functions, then basically, if we've been using a lot the function and the entropy pool is depleted, let's say, then it will fail the entropy check and it will not give us the random values. Now, the author of the book makes a very interesting point here, and it explains how it's a very bad idea to use this blocking pool, to use the random instead of urandom. Why is that a bad idea? Well, first of all, according to the author, the entropy estimator, so the entropy check, the algorithm that powers the entropy check, it's weak and it's unreliable. So either way, you're checking something like not in the best way, and the result you get might not be accurate. That's the first point. Let me see, reliable. A reliable entropy check. The other problem is that there is a denial of service risk. Why? There's a denial of service risk because basically if a lot of operations are, let me close because the cleaning lady might walk in a little bit. There's a denial of service risk because basically what's happening, if a lot of applications are calling random and the entropy check fails, then every application has to wait until the entropy check passes again. And so an attacker can exploit this to create a denial of service condition, okay? So according to the author, always best to use a non-blocking pool, always get your bits, and then I guess perform checks on your own rather than rely on this blocking pool because of these two reasons. Again, the unreliability of determining the entropy of the entropy check itself, and the denial of service risk of blocking the distribution of random bits to all the applications in the operating system. So we've talked about Unix, and now let's talk briefly about Windows. Okay. In Windows, we have something called CryptGenRandom. Let me sure I'm spelling it. We're gonna spell it the right way. CryptGenRandom. Okay, which is legacy and was now substituted by CryptGenRandom. Old. No more. B CryptGenRandom. B CryptGenRandom. There's no O. Sorry guys. B CryptGenRandom. Okay? So again, the BGenRandom. So basically, this is the way that Windows does the things, and so we're gonna have a. Sí, puede. Gracias. So we're gonna basically have the CryptGenRandom, which was the old function, deprecated. I'm gonna put like an X here, in favor of the bCryptGenRandom, and then we're going to also show. I'm gonna show the code also on the demo on the computer. And what else can I say about this? The way the Windows generator works is that we have a kernel driver called cng.sys, and cng.sys is the kernel driver that provides randomness, random bits. Okay, so basically, what is it? Exactly. So it's loosely based on Fortuna and it provides random bits. Okay, perfect. That's the job of this kernel driver. And something also I forgot to mention, if you want to see the actual C code that powers the implementation of Unix, you can find it in, let me see if I can write it down super fast. It's going to be in the Linux kernel driver, drivers char random C. It's gonna be source code. Driver, where is it? Drivers char random C. Perfect. So this is gonna be little. If you want to see the C code that powers the random function, you gotta go into root, drivers char and random C. So let's go back to Windows. Nothing really I want to say too much about the Windows one. It's again the cng.sys driver gives you the entropy values, and it's loosely based on the Fortuna algorithm that we mentioned in a previous class. So this covers a little bit some real-world application of software, pseudo-random number generators. Now let me take a break let me go out from the board for a second and let's go to the computer where I will show the source code of some of these algorithms we talked about. Okay, so I'm gonna interrupt now and let's go to the computer. Alright guys, looks like we're recording. We're on the computer now. We're just gonna briefly look at some code samples that I took from the book and I put them in my IDE so you could see them better. Alright, let's start. I don't know if you remember, but I mentioned that when talking about the Unix, we're talking about Unix software-based pseudo-random generators, right? And so in order to, I said that, we could just need to read, let's see, devrandom, okay? As you can see, devrandom, we're just reading it as a file. It keeps giving us random bits, okay? So I'm gonna stop it. Okay, good. I stopped it. And now we can do the same thing of urandom. Same thing. I'm gonna stop it. Okay, so I can read it as a file, literally, even from the command line. Head. Let's do this. So it only gives us a little bit. And so yeah, that's the logic. There's this file called in devrandom. I'm on Mac. I'm not in Linux. It has the same Unix kernel, but it's a bit different. but the principle is the same. We have dev-random, which is a file, and we can read it, and whenever we read something of it, it will, if we keep reading it, it's going to keep, as you can see, it keeps giving us random values. Or we can read a little bit of it, like I did with head, etc., etc. So if we were to write a code, a C function that lets us return X bytes of random values, we would do them in this way, right? This is the naive way, okay? And so we would open the urandom with a read only, and then we're gonna read as much as the buffer size that we provided as an argument to the function. Then we close the file, return 0, etc., etc. We save into the buffer. But this is a very naive, and it's not a safe way. Why? Because we're not performing safety checks, right? For example, we're not even checking if the return value of open right here is good, or if it's or if it's not being if the value is filled with zeros or left unchanged. We're not checking for anything here. So guys, let me show you the safer way to write a C function that returns random bytes. Don't get scared, okay? And the code, I got it from the author gets it from the LibreSSL library, so it's a established library. And this is the better way. Take a deep breath. Boom. All right, so here we're definitely especially in the, let me see, where's the open call? There you go. We have the open, and then immediately we're checking FD. We're checking all the possible, we're doing all the possible safety checks. For example, again, here, there's a check on the call to open. And then, what is the other? Here, there's a little number. And then here you have the check, even here. Oh boy, battery low. Hold on. Good. And yeah, so it does safety checks. That's the big difference between the naive and the safer one. Okay, lots of sanity checks and verifications. Okay, so this is the proper way to write a C function that returns random bits. Safer way, meaning that it's harder for an attacker to manipulate this than to attack and manipulate this. Again, pseudo-random number generators are very important for all the cryptographic security, especially if they're used for key generation. Okay, let me see if there's anything more that I have to say. Yeah, so also I talked about how the difference between dev random, right, between these two, how this is part of a blocking pool and this is part of a non-blocking pool. So there's an interesting script that the author gives that basically I cannot run this script because in macOS it's not the operating system that does, it's not the kernel that gives random bytes, but is this algorithm called Yarrow. So Yarrow is the one that takes care of giving random bits, so there's no such thing as this in Mac. This file is not available. I would have to be on my Linux virtual machine to be able to run this script. So let's pretend we're on Linux right now. What this script does is basically, can I say, it reads the current value, it reads the entropy availability value and saves it in estimate, and then it depletes, minimizes this entropy value by reading 4 kilobytes right here, by reading 4 kilobytes of data, okay, from dev random right here, and it waits until the estimate, right, until the estimate is less than 128, and then it starts, it reads another 64, again, what is it? It reads other bits, okay, and then 64 bits, so 8 bytes, again from DevRandom, and it prints the estimate again. Unfortunately, I can't run this, but it will basically show how some, let's say this is the execution. It shows how first the thing returns some random values, and then the entropy value is low. Then it prints this, and then it prints this. It increases, it increases, it increases, etc., etc., etc. And so try it on your Linux machine, and this will give you a will make you understand really well what is this entropy check and this entropy value that is used by DevRandom, you know, when deciding if it's okay to provide random bits or if it should be blocked and not provide them if there's not enough entropy. And again, citing what the observation of the author, it's really not a good idea to use it, and not a good idea to use it because again, it's more problems. It introduces more problems than what it tries to solve. Very interesting view of the author. And that's it. And then lastly, we're going to look at the Windows version, Windows CryptGenRandom. Okay, and again here it's a C++ function. And what's in, again, there's like checks here, right? If that means we're checking for stuff right here. What's interesting about this code is that you have to call this, you need to declare a cryptographic service provider, okay? And then, which is right here, where is the crypto provider? Yeah, this one, a service provider. And then you have to create what's called a cryptographic context, encrypt acquire context, okay? This means that, like, you know, there's a bit more chances of things going wrong, especially if this crypt acquire context is not defined correctly, or if it fails silently without notifying the user. Then you're gonna have, if this context is not implemented well, or it fails, or something happens, then you're gonna have suboptimal randomness, right? Less randomness, and the user won't even know. So that's the problem that the author mentions with the CryptGenRandom, and that's why in the new version, this is the old one. In the new version, so the new what's it called? The CryptGenRandom, the newer one, right? Does not have all these, basically does not require the code to open a handle, okay? So it makes it easier to, it skips a few passages, doesn't introduce as many errors, or at least chances of errors as this one. So I think it's pretty interesting to see all of them. This is the code that powers these things. Now let's go back to the board, finish this this topic. Sorry, finish this this video with we're talking about hardware pseudo-random number generator. So I'm gonna stop here and let's go to the board. Yes, we are finally back on the board. So we saw some real-world example of a naive code implementation, the short one but insecure, and then the proper code implementation, the nasty one that I took from a real cryptographic library that does a lot of checks when reading random and urandom. Okay? Then we saw the script that checks for this, you know, for the blocking pool that checks this, the entropy value. We saw how to go in Linux and print out the entropy value for all the, for the blocking pool. That was the shell script. And then finally we saw the implementation of CryptGenRandom, and we saw how there's a whole thing about creating a context and things that that in history made programmers implement this thing wrong. And then we saw how we didn't see the code of this one, but we talked about how this one makes this one more secure by abstracting some things that were causing problems. And this kind of takes care of the software pseudo-random number generators. What about the hardware ones? Let's talk very briefly about this. And let's make an example of the, so hardware means they're physical parts of devices, physical devices that are embedded, for example, in the Intel processor. And actually, before I, yeah, there you go. It's called Intel Digital Random Number Generator. Okay, the Intel Digital Random Number Generator, and this is basically something embedded into the Intel chip, okay, in the processor chip. And so you guys know that you talk to the processor in assembly language, and so in assembly language Intel gives us the RAND. Is it called the RAND? Yeah, RDrand assembly instruction. Okay, RDrand assembly instruction, and this it's something that you call into assembly. Right? Assembly is a way to write. Is basically the so you have, when you write a program, you write a C language, and then the C language gets compiled into assembly code, which then gets linked, blah blah blah, and then becomes machine code. Okay, C is what we saw on the computer. That's what it looks like. Assembly is a bit more nasty, and it deals with literally filling up memories, registers and memory slots, and giving values very low level. Like a few lines of C are probably like 30 lines of assembly. I'm giving like a estimate. And then machine code is like literally all zeros, 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 and ones, and is what actually gets read by the processor. Okay, so the assembly instruction RDrand is provided by the Intel processor chip, and that part is called particularly Intel Digital Random Number Generator. And so how do you call this instruction? You call this instruction by providing a register. Okay, so you provide a register to RDrand, an 8-bit, 32 or 64-bit register, and RDrand will put into the register the random data. So then you can read it from the register. Once you have it in the register, you can do whatever you want. It's like if it's saved in a variable. Not the same, but that's the gist of it. So RDrand, okay, and it's very fast. This is very fast because it's, you know, hardware, and you're talking already with the chip. Let me see if there's something else. And okay, how does this hardware random number generator works exactly? So in hardware engineering terms, I need to read this from the book because it's a dual differential jump latch with feedback, right? So the entropy source I can do this, I can write this. It's a dual differential jump latch. Okay, dual differential jump latch with feedbacks. The hardware engineers know what I'm talking about. I'm not an hardware engineer. I'm not exactly what is this, but if I can simplify this, using simple words, it's basically a small circuit that jumps between 0 and 1 depending on thermal fluctuation. So a little piece of electronic that literally jumps from 0 and 1, and so literally since it jumps from 0 and 1 as a status depending on the thermal fluctuation, it means that it will give us randomly either zeros or ones all the time, right? Because we can't control the thermal fluctuation in this circuit, right? So this is where the Intel Digital Random Number Generator, a hardware-based PRNG, gets its entropy. And again, we can call this from assembly, or C programs call this from assembly, using the RDrand command, okay? You pass to the RDrand command the register that you want to fill up with random bits, and the processor will get its random numbers and fill up the register that you told him to. There's also another instruction called rseed, which instead of random bits, it returns also an assembly. Right? Also an assembly instruction will return, this one returns raw random bits. Yeah, raw. How does the book define? Because I mean, both of them give random bits, but the rseed in particular. Let me see, 1 second. Let me just find it really quick. Yeah, rseed. There you go. Right. Okay, yeah, there it is, rseed assembly instruction. So the rseed assembly instruction returns random bits directly, okay. Okay, it returns them directly from the entropy source, okay, the rseed. So this is useful if you have your own cryptographic function implementation, you want to seed, if you want to seed yourself other pseudo-random number generators, okay, you're gonna use the rseed. Perfect. Now we know this. Last thing we need to know about this Intel implementation is that after you call these assembly instructions, there is a flag value called carry flag. Okay, and the carry flag means just is a value that is either 0 or 1, true or false. And the carry flag will be set to 1 if the data is valid. Okay? Perfect. If the data is valid, if it's 1, data valid, and the randomness is good. Okay? It's a check that the processor found. But if the carry flag is 0, then the data is not too good. So it's something that should always be checked. And I think though that, let me see. Okay, but I mean, unless what this author says that, which means you should arrangement the value, otherwise you should be sure to check the CF flag if you write assembly code directly. So I mean, nobody writes assembly code directly, so but just to know, the part of the process of getting random numbers for this hardware pseudo-random generator of the Intel chip is also to check a carry flag. Okay? Oh, I shouldn't square this because then it looks like an instruction. Very good. And this pretty much concludes the section about pseudo-random number generators. Maybe a fun fact about the hardware Intel, there was a little bit of fear after the Snowden revelation about possible backdoors into the Intel chip, which basically mess around with this randomness, right? So if the the best way again to plant a backdoor in an Intel chip would be to tamper with this, or you know, release a certain version of this chip so that you can really guess the keys, and then again, this is how important random number generation is. This is literally the origin of the randomness, is the origin of your keys, of your future encryption. So if you have a backdoor Intel digital random chip, then everything you're gonna generate, all the keys you're gonna generate, everything they're guessable by the person that planted the backdoor in Intel. So if you're really paranoid, the author suggests to use RDrand and RDseed not alone, but to mix them with another source of randomness, of entropy, maybe another hardware, I don't know, whatever it is, but not to use solely alone these ones for hardware from Intel. No, mix them with other random. You should kind of mitigate the risk of backdoors and everything. And again, just a little curious parenthesis, a little side note about this, about backdoors and things like this. Very interesting, I think. But basically, we're done with this real world use of pseudo-random number generators. Remember, software and hardware we talked through, and that's it. So next video we're gonna look at when things go wrong. So again, we'll see where things go wrong in this process of generating random numbers. Thank you for watching. Subscribe and like to support, and leave me comments, please. Feedback, good or bad, I really need it. Okay, thank you guys. Talk to you soon.